it is 6 on the dot. I think we can wait for another 2 minutes just for people to start rolling in. Moshe, is that okay?
Yeah, that's cool. Maybe while we start, if anybody has any interesting or funny or not so funny failure stories that they want to share quickly, not to put anybody on the spot or anything. I'll send out a free t-shirt if anybody gives a failure story.
So while we're thinking, so I have one, right? This happened quite a few years back. I think it was Kubernetes version 1.10 or 1.11. So our server was actually running version, I think 1.10. But my kubectl client on my machine is 1.13. And initially I didn't know it because I installed my kubectl via brew, and I normally just brew updates, and that just completely slipped my mind. So I spent 2 days debugging this issue, and it was just a problem with my client. It was just too new compared to the server. 2 days, 2 full days.
Yeah.
Yeah.
Only 2 full days.
Oh yeah, only 2 full days. Yeah, exactly. But yeah, so that's, I don't know if it was funny or not, but it was definitely horrendous experience.
I think we lost Harry's
I
audio.
just deleted the Nginx ingress on prod instead of dev, so that was fun.
Well, I think if you haven't deleted something on prod instead of dev, you haven't actually spent enough time in operations yet.
Very true.
Yeah. So I've done that a couple of times, not too many. I'll actually talk a little bit about something I did recently that was a little bit more serious than that, but didn't turn out too badly in the end.
All right, so I see that it is 3 minutes past 6. I think we can start. So just before we start, just want to do some housekeeping announcements. So this, as everyone has already experienced, this is an open session. Means that you can unmute yourself if you want to talk. But I think throughout the session, while Moshe is presenting, let's refrain from doing that. I think we can just keep all the questions to the end of the session. I think, Moshe, you have a Q&A session, and then we'll just answer all the questions then, just so not to disrupt the flow of the session. This session is scheduled for an hour. However, we will leave the Zoom meeting open if people would like to continue their discussion, or if there's a lot of questions. But this is scheduled for 1 hour. As we mentioned in the event, that the technicality rating of the session is 3 out of 4. So it is quite Kubernetes specific and geared towards an audience that has some sort of Kubernetes experience. But you're also welcome to join to listen in if you don't know anything about Kubernetes, right? Questions are always welcome, but again, we want to keep them on topic. So please remember that. You can also ask your questions in the chat panel. If you're scared that you're going to forget about it at the end of the session, you can also just put your question there. We'll also refer to them. This session is being recorded and moderated. So please be respectful towards the speaker and your fellow participants. You will be kicked out if you do not abide to our code of conduct. I see there's more people. I'm just going to admit them quickly. Yes, so there will be a poll during the session. It's just 3 simple questions, and the purpose of these questions is just so that we can understand you a bit more, and we can deliver more relevant talks in the future. So please, if you do get a chance, just answer these 3 simple questions. It's a multiple choice question. It's quite simple. And I don't know how we're going to do this, but at the end of the session, we will do a draw. Yeah, so I'll find a way to actually do that. Basically, if you still stay till the end, you will get a chance to win a JetBrains license to any of the JetBrains products. Okay, so and that is thanks to our JetBrains sponsor. And that's it. Okay, to you, Moshe.
Cool. Cool. So we are going to deviate a little bit from the agenda, or the published agenda, not too much, but hopefully it will be for the better. Cool. So a little bit about me. So I'm a Kubernetes fanatic. Caught the bug a good couple of years ago, and I've been going Kubernetes ever since. In my spare time, I spend quite a bit of work working upstream in the SIG cluster lifecycle group, which, if you don't know, SIGs are the Kubernetes way of creating microservices within the Kubernetes organization, so to speak, to break it down into smaller pieces that are manageable. And then I also enjoy quite a bit of psychological safety and resilience engineering, which I am going to talk about a little bit now, because I think it actually makes a lot of sense in terms of speaking about failure. In terms of Kubernetes, is to kind of define what failure means and to change the lens at which you look at failure. So there's a couple different ways in which you can look at failure and view it and appreciate it. And I'll give a 40,000 foot view on the resilience engineering perspective of failure. I'll then go through a few of the common themes from failures that are published on the k8.af website, as well as a couple of my own. And then I'll end it off before a Q&A with a demo on how you can use Open Policy Agent to mitigate some of these failures or prevent them. When I was a little bit younger, a little bit more naive, a little bit more time on my hand without any kids, I picked up this book in a library or in a bookshop. And it basically goes through how Copernicus, Galileo, Newton, and Einstein built upon the works of the people before them. So they're built upon the works of the people before them, and this talk is going to follow along similarly. So sorry, I'm just going to mute. This talk is going to follow along that theme. Most of the work that I'm presenting here is not my own. There's a bunch of giants who I'll introduce now who have done most of the hard work. I'm just reintroducing it in a little bit of a different format and a little bit of a different context, but I take no responsibility for the work itself. It is from the giants. And the giants themselves come from, so we're going to look at it at a little bit more than 50 post-mortems. So we're going to look at 3 decades of post-mortems, if that's actually possible. But it is possible through the lens and research of these 5 and 6 giants. So if you're in the resilience engineering community, you'll recognize them. If not, I'll introduce them. So we have Dr. Eric Harlenagel. He's, I think, the only academic in this group. Richard Cook is a medical doctor. I think he's an anesthetologist who now, he probably doesn't know how to use a computer. Maybe he does, but he wrote a document about 25 years ago that is more relevant to how IT systems fail than ever before. John Allspore is the former CTO at Etsy, and he's kind of the person that brought resilience engineering and safety engineering to the IT community and the infrastructure community. Dr. David Woods, I think he's also a doctor, medical doctor. He's definitely a PhD, and he spent most of his work time at NASA investigating shuttle accidents and the like. So David Woods and Eric Hollenagel spent quite a bit of time doing a lot of research together. Sidney Dekker is a pilot, was a pilot, and he does a lot of talks on human factors and system safety. And then closing out the pack is Henning Jacobs, who comes from Zalando, which I think at last count they had over 200 Kubernetes clusters running. And he's done a really good job of collating a whole bunch of post-mortems into the website k8.af, which a lot of the data is coming from. So this is Eric Hollenagel. He's done quite a few books, which he has co-authored with David. Richard Cook wrote this document, How Complex Systems Fail, in 1998. So he wrote this not about IT systems. He wrote this about primarily medical systems. And all of these characteristics, so there are about 18 characteristics of how complex systems fail. And he wrote it all about medical systems, medical environments, operating theaters, ICU wards, and pretty much all of them apply even more so towards infrastructure, Kubernetes clusters, application environments, business environments, anything that can be considered a complex system. So it applies also to biological systems, but this is really, really relevant, and it's perhaps the root of everything in resilience engineering in the context of complex systems. So John Allspaw, he also produced this model of above the line and below the line thinking that splits the work that people do at the sharp edge, and the sharp edge being during failure. And he says that there are differences in the way people think about systems and the way they actually occur. And there's this disconnect. And he calls this the above and the below the line things. And he also did quite a lot of research on the Snafu project and the Stellar report, which highlights a bit of a more in-depth research into this area. Sidney Dekker is the pilot. He's got a series of videos on YouTube that are actually quite short and quite nice, that introduce some of his concepts that he's introduced, the primary being just culture. So in his book, he told the story of I think it was a mechanic at an airline who, through one way or another, was found to have performed the last maintenance on a part that turned out to be defective and caused an aviation accident. And rather than throwing the book, so to speak, at him, the company didn't do that. What they did is they asked him to tell his story and to account for what he did. And by telling the story and accounting for his actions, that was the way in which he took accountability for what happened. So there's many different ways in which justice can be meted out, and Sidney Dekker provides quite a lot of framework for doing that. So when we speak about failure, so it can mean different things to different people. I'm going to give you the view of Richard Cook and Rasmussen, who developed this model that basically models every single failure that occurs. Doesn't matter where that failure is, it will always follow this type of model. in complex systems, biological systems, social technical systems. They all follow this model, and the model starts with a point in a space that is bounded by 3 sides. So on the one side, we have a boundary of unacceptable costs. So if you spend more money than you have, you're going to go out of business, and that's a failure. So a failure doesn't necessarily have to be a server going out. It can be you going out of business. On the other side, we have unacceptable effort. And this could be burnout, it could be low retention, lack of being able to hire the right people. So if people are being overworked, you're going to fail on that front as well. And then we have the more common front on which failure tends to occur, or not to occur, but to be observed and seen. It's on where the performance. So if your system is not providing the functionality that it's designed for, that's an unacceptable performance. So when and so within this boundary, these 3 lines and three boundaries are not static. They will move up and down inside the system. So on the one hand side, your accountants are always going to be pushing you to save money, and they're going to be saying that we're going to run out of business in the next month, the next year, everything costs too much. On the other side, people are going to burn out. Keeping morale up is always a struggle. So these lines always move, and then your incidents and your failures come along, and they will then impact this line of performance as well. You also get your unexpected blue moon and black swan events. So Corona is a good example of this, where it not only makes a minor movement of the line, but it's actually going to change the game completely. And before, you might have had acceptable costs at X, and now that line is moved completely. And this is the way in which the scenarios in which failure occurs. So it's not in a static world, it's in a world that is constantly changing, where the boundaries are constantly changing and the conditions are always changing. So when we define failure, we're really talking about this point in a complex system that moves around, and as soon as it's moving around within the system, and it will move towards a safety boundary. And this is the boundary at which people expect that crossing the boundary can cause a failure. So for example, if you have a highly available system and you have a primary and a slave server, if your slave server goes down, then you're crossing that boundary. And you do that often enough, and maybe you say, why do we even need the slave server? It hasn't caused anything. So this is what Sidney Dekker talks about when you guys drift into failure, where if you drift over this boundary line and you stay there too long, you could mentally move that safety boundary close towards the edge, and failure will become much more possible and predictable. So moving outside that edge, that is what we kind of define as a failure. So a failure, there's a number of things that we can take out of this. One of these is that if you look at chaos engineering, so chaos engineering is a subset of resilience engineering. And what that really is trying to do is map these 2 boundaries. So your safety boundary and your actual hard boundary. So if you're performing chaos engineering in production, you're going to be moving that boundary line and moving your operating point past that safety line to make sure that is in fact where the safety line is, and it hasn't somehow moved forward or backwards a little bit. So chaos engineering and resilience engineering have a lot in common, but they're one is a subset of the other. What really this brings home is that failure, there is no root cause of failure. It just does not exist. And the reason why there is no root cause is because a failure just happens to be a point in time at which you are operating beyond a boundary. The problem is that boundary changes from day to day. Your operating point changes from day to day. And you can never go back in time and replay that in the exact same situation. So a lot of root cause analysis looks at why people did the things that they were doing to try and teach them to do something different when it happens again. The problem being is that no failure will ever happen again. They always happen in a distinct complex environment, and that complex environment is never going to be repeated. So this is kind of the point that resilience engineering tries to make, and they try and make it within inside the regulated industry, so aviation and space, and they are succeeding a little bit, but it is still a little bit newer in those fields. The IT field has been taking it on a little bit better with things like blameless post-mortems, which really understand this concept at a fundamental level. So if there's no root cause of failure, and failure, we can't look at past failures to fix them and prevent future failures, what do we do about that? And Richard Cook highlights the kind of differences between what we should be doing and what we currently do, and what will enable us to be more resilient. So many systems today are built for high availability and robustness, but those are things that do not help prevent failure. They can prevent known failures, and they can prevent known failure modes. But if you agree with the resilience engineering model, then we don't know the failures that are going to occur because they're never to be repeated. Each failure is unique. So building a highly available system doesn't really help you that much. You can do it, but if you design for that as the end goal, you're going to be left with a fragile system. And what you really want is to build a resilient system. And in a resilient system, we understand that the boundaries are moving. We understand that the operating point is moving, and we want to react to those boundary point changes quickly. So when something like COVID happens, we want to be able to react quickly and change operation. When a server failure occurs, we want to be able to react quickly and recover from that. When an availability zone goes down, we want to be able to recover from that quickly. And so these are the principles on which you build a system to withstand failure. And when you look at how Kubernetes was designed, Kubernetes was designed with all of these things in mind. So withstanding transients, recovering from failures, these are all things that are built into the Kubernetes model that allow it to behave in the way it does, and provide a very strong platform for building resilient systems. So how do you do it? So there's something called the resilience cycle. It's a little bit essentially like plan, do, act. So you are always going to be within an operating mode, and then you'll have some pressure or resistance on your boundaries, and it will force you to operate a little bit closer to those limits. At some point, you're going to start seeing degradation and potentially breaching those limits. You see a failure, you need to adapt to those failures, build new capabilities, learn from them, and repeat. So this is the resilience cycle. So which covers the chaos engineering type concept at a higher level as well. So to summarize on the failure in the context of resilience engineering, we understand that there's no root cause. You need to trust your operators. So you need to trust the people that are working on the system to make the decisions to, when those boundaries change, when those operating points change, to make the decisions to adapt the system to the current working environment. And I'll show you a little bit about what that means in a little bit. And one of the key things here is, in order to be able to do this, you need to expose your control surfaces and the knobs on which to turn them and to configure and customize the system, because you can't know every situation that will occur. You have to design the system to adapt. And the only way you can adapt successfully is if you know the state in which the system is, and you can make changes to that system simply and by seeing the feedback quickly from it. So these are kind of the core principles of resilience engineering and how they impact on failure. So one of the key things about trust your operators is this thing called the Westrum organizational culture. So this was something that Jez Humble introduced in continuous delivery quite a while back. We perhaps didn't introduced it, but he promoted it quite a lot. And Westrum highlights, I think Westrum again was also in a medical context, about 30 years or so, and he highlighted 3 different types of organizations. And to build a resilient system and to build a system that will recover from failure, and where those boundaries are well defined and accurate, you need to be on the generative side. And this is really about how you talk about failure. So in a generative organization, you're going to have messages who are reporting failure. They're going to be promoted and they're going to be trained. And failure is going to lead to inquiry rather than justice and scapegoating. And when novel ideas come to the front, they're going to be implemented and they don't lead to problems and get crushed. So these 3 different organizational cultures have a lot to do with the DevOps type organizational culture transformation, but without them, it becomes very difficult to build a resilient system that doesn't fail. So that leads us to the end of part 1 on the high level part. Now we'll dig a little bit deeper into 3 years of Kubernetes post-mortems. And these post-mortems come courtesy of Henning Jacobs again. So there's this website and a GitHub repository in the back. So you can actually submit a pull request to submit your story. I actually have to submit a couple myself. But I suggest anybody who has nice, fun stories to submit them as well. And so what I did was I took these stories. There are about 60 or 65 unique events that are described here. And then I kind of classified and categorized them and coded them so that we can develop some insight into what types of failure occur, what are the general themes that happen, and what can we do to build our systems a little bit more resilient to cater for them. So if you look at the contributing factors, so there is no single root cause. So many of the time, issues are encountered in multiple dimensions. So you'll have a cascading failure, you'll have a resource constraint combined with something else that results in your undesired outcome. So we highlight these are the kind of areas upon which failure can occur, and we'll dive into each one of these independently. We also had a look at what type of failure occurs. And most of the failure was a full outage, so loss of functionality. But we also see a lot of performance related and partial outages on Kubernetes, which is a good thing. And I think the trend over time, so this goes back about 3 years, the data for 2020 and 2019 is still a little bit short, but you can see that the trend is a little bit towards full outages becoming less common and partial outages and performance related outages increasing. And when you have a performance or partial outage, at least you can deliver some value and you can mitigate a lot better. On the other hand, they're also a lot more difficult to detect. So performance-related issues are notorious to detect, partial failures as well. So a bit of two coins of the story then. And I'll actually come back to this, some implications of this a little bit later on. So our first type of failure, failure mode, is it's probably, this isn't really unique to Kubernetes. So most operations is really about dealing with resource exhaustion and decompensation mechanisms within the system. So what this will look like inside a Kubernetes environment. So if your pods are getting killed, they're failing to schedule due to lack of resources, they're getting CPU throttled, IP pools getting exhausted is a fairly common one. There's quite a number of ways to inflict a denial of service on you. Malicious denial of service is also increasingly common, and thundering herd, which is a self-inflicted denial of service. So these are all of the kind of some of the symptoms that you've exhausted resources in your system. And there are a couple of ways to deal with it. So the first plan really is, and this is coming back to the resilience engineering view, is that to build a resilient system, you need to be able to adapt, and you need to be able to prioritize what you want to be able to deliver first. So when your system comes under resource constraints, you need to be able to load shed. And as much as we make fun of Eskom for load shedding, they are actually making the power grid more resilient. We're lucky enough that the power grid actually hasn't failed. They have done a lot of load shedding, but we haven't had a failure which would, as far as I know, result in like a 2-week full country outage. So know how to load shed and agree upon in advance with your stakeholders to know when we have an issue, we're going to start taking these services offline first in order to protect these other more critical services. So that's kind of lessons learned from Eskom, unfortunately. Always over provisioned control planes. So as a dynamic system, if your Kubernetes control plane comes under load, it can cause a lot of problems. So, and it's not only particularly relevant to Kubernetes, it's relevant to any control plane. So for example, AWS, who don't particularly use Kubernetes a lot, they always provision their control planes, which as far as I know are all bare metal, to no more than 50%. So they never breach that 50% mark on their control planes. And this is for their core critical services. Their workers and their data planes, I think they go all the way to 100%, but on their control plane, they will never breach that 50% mark. So always keep additional capacity for your control plane, and more is always better for the control plane. That means less than 50% CPU usage in a Kubernetes environment. Another one to keep into mind here is, especially for etcd, is disk latency. So in AWS, that this might mean provisioned IOPS, or it might mean taking a multi-terabyte disk where you're only using or in Azure, for example, it might mean taking a multi-terabyte disk where you're actually only using a couple gigs because you need the IOPS. So always over provision the control plane. Another one here is go with 5 etcd members or more. Going down to losing one etcd member and having to perform maintenance on another, or performing maintenance on a member and then losing another, results in very unhappy days and weekends. So 5 is always better than 3. Choose 5 when you can. It does make your life a little bit easier. It does increase latency a little bit. So latency with etcd does go up, as far as I know, with each additional member, but keep your control plane safe. And then provision the data plane to withstand the loss of end fault domain. So really, this comes down to fault domain analysis. So understand what your fault domains are. Test them with chaos engineering to understand where those fault domain boundaries lie, and make sure that you have enough resources to cover that. So in AWS, this could mean running an additional region with capacity up. So some people can run in an AWS region with the assumption that if the region goes down, they can go to a new region. The problem with that is that when they do that, that entire region has the same idea, and you then get throttled behind a very long queue. So if you do need to be region aware, that means you actually need to run in both regions at the same time, even if the one is just reserved. The same kind of applies to availability zones. Make sure that you can survive the loss of an availability zone without going over that 50% CPU usage on your control plane, and also without going too high on your data plan and your worker nodes as well. Another one that can hit you if you're running in a cloud environment, and even in a vSphere environment, understand the rate limiting that applies. So I know, for example, IAM has rate limits applied to it. ECR has rate limits applied to it, and pretty much any upstream system, large upstream system is going to have rate limits applied. So understand what those are, and ideally monitor them and see where you are within those levels. There's a use method promoted by Brendan and Greg that looks at utilization, saturation, and errors of any component in the system. So looking at the utilization level of your rate limits is something to keep in mind. It applies on the vSphere as well. So if you have noisy neighbors on your vSphere or vCenter environment, that can impact you. So a vCenter, even if it's running across multiple clusters, can apply rate limits and impact your fault tolerance. And then the same applies downstream. So always apply resource quotas, limit ranges, and custom policies. So don't let your consumers create a multi-terabyte pods with 1,000 CPUs and quickly consume all of your resources. You can do this with config maps, secrets as well. So if you have processes that are generating dynamic secrets and processes, this can come into play as well. So rate limit your downstream consumers. Second up, in terms of themes for failure, and it comes down to, this is how I feel whenever I'm upgrading Kubernetes. It's like changing the wheels on the bus as it goes. There's actually the way in which to perform an immutable upgrade on Kubernetes using immutable nodes actually requires 3 independent images and a coordination that rolls the first 2 before replacing the third. So upgrades can be quite tricky. It is getting better, but upgrades are also where failure occurs often and most often. And it's not unique to Kubernetes. It's just the old adage of deliver small changes more frequently applies. So one of the reasons why Kubernetes is on a 9-month release cycle of 3 releases is because of this belief that you shouldn't leave a cluster too long, because then the scope of changes that you're applying to it is going to grow too large, and then you're going to push it off a lot longer and longer and longer until eventually you're using long-term release and end of life cycle products. So upgrade early, upgrade often, but test your upgrades. So one of the failures that Zalando that happened to Zalando is they have a full infrastructure pipeline that will test the configuration and infrastructure of every release that they deploying, except they had a failure the one time where the failure was only visible on an upgraded cluster. So always upgrade to your last version or deploy your previous version and test the upgrade to the new version as well. So upgrade testing is important if you are running in place upgrades of clusters. Don't let pods sit around too long. So consider a policy of terminating them and scaling them up and down and replacing them on a regular basis, just so that they don't get stuck in their ways, and don't use any crutches. There is a long-term working group within Kubernetes that have been trying to put a policy and process in place that will allow long-term releases. So this is 1.16 initially was not a candidate for this, but with Corona, the next version of Kubernetes has been delayed. So 1.16 by default will actually get 1 year of support. They will, as far as I know, 1.19 is a potential candidate for the next version that will also get 1 year of support. But there's still quite a bit of debate around this. But it's likely to move to 1 year pretty soon, which is perhaps a little bit of breathing room, but also perhaps don't use the breathing room because it is a bit of a crutch. Next up, we have networking. So networking failures are pretty much are really common. And inside the Kubernetes world, they're increasingly a little bit more fun to deal with. So there's actually a project from Bloomberg, I think that's called Cold Pinger, that will ping, provision a pod on every single node in your cluster, and then ping every other node to make sure that you have a full mesh of connectivity between all your nodes. It's no fun spinning up a pod and then it not being able to talk to anything, but being able to talk to DNS, and things start going downhill pretty quickly from there. So a couple of key points here is monitor your control plane. So all of the CNIs will have some level of metrics being exported from them with Grafana dashboards available. Look at them, make sure that you understand what their capacity levels are and what resources they will consume and what exhaustion looks like. Also, spend a little bit of time looking at the data plane for your CNI and understand if you need to trace a problem from a pod all the way through, that you know where to look. So understand how kubeproxy works with service IPs, or eBPF if you're using one of those implementations. So understand how you can trace those data paths to understand failure. And then also another tricky one is if you're trying to do rolling deployments, these are actually doing them without any loss of connectivity is actually not as easy as it seems. So there's a talk by Lee from Weaveworks, which was actually a very, very good talk about describing all the different things that you need to do in order to get a zero downtime deployment. I would suggest having a look at that if you can. And then we come to DNS. So DNS, it is always DNS even when it's not. So in Kubernetes, as we all know, DNS takes a much larger role for service discovery. And if DNS fails, many other things fail. So one of the common issues is denial of service on DNS. And again, the kind of the same concepts apply. Over provision your DNS infrastructure. Make sure that you have more than enough capacity for it. Be wary of the ndots issue. So there's a link at the bottom there, but essentially you can be actually performing up to 10 times the number of DNS queries for external services if you don't bring your ndots down. So have a look at that one. It can cause issues. And then also consider a local DNS cache. So Node local DNS does this quite transparently, and it did recently get GA'd as well. So it does lower it, I think, as much as 50 or 60%, depending on your environment. Also reduces your contract usage, which helps a lot with your service IPs and DNATing as well. And then we come to perhaps the last one, so user errors. So if we're never going to get away from these. So these occur both as users of a platform and users of Kubernetes, and as consumers. So for example, the one nice snafu that I did a couple months ago was delete the wrong cluster. So in one of the places where I work, we have a provisioning infrastructure that will allow us to deploy and terminate clusters on demand. And so I was upgrading an environment or one of those clusters to a newer release. So I terminated the cluster to bring up a new one. And as I did that, the alarm bell started ringing, and I realized I terminated the wrong cluster. And that was the beginning of about a 2-hour window where we had some major issues, and it tested our backup process. So replication isn't backup, it's another one. So we had to perform a restore from backup, and it was a lesson learned, and we implemented termination protection on the clusters that are stateful, but always be wary of yourself and the people using your system. And this is kind of where open policy comes into play, and policy enforcement. So if you ask who's at fault for deleting the wrong cluster, so is it the user who deleted the cluster? Who's at fault for deploying a pod that requires 1,000 CPUs instead of 1,000 millicores? And the answer is it's not the user, it's the system for allowing it to occur. And this is where we implement policy to make things work better. So some of the more common ones are always apply requests and limits on your resources on pods. So don't don't allow defaults or enforce defaults using a limit range. Ensure that you are not allowing too many of resources. So don't allow people to create 20,000 config maps of a meg each, or however big they can go, and take down your etcd cluster. Or likewise with load balancers, don't let people create 100 load balancers, one for every pod. Apply some sensible defaults there and bring them down. Another interesting one is the deployment strategies. So depending on how many replicas you are using for a deployment and the strategy that you're using, you can double the number of pods being deployed. So if you have high replica counts, implement some policy to reduce the size of deployment strategies. So I can give an example of one of these a little bit later. And then apply, there's node anti-affinity. I did see somewhere where you can use an admission controller to inject these automatically. I must just find the link for that again. And then there's also a newer one that was introduced or GA'd, the topology spread constraints, which let you apply affinity across multiple zones. So place a pod in every AZ, or one, or evenly amongst AZs, if that's required. Coming back to the impact of failures and the mode of failures. So one of the things that we looked at was where on the clusters that failed, whether running a hosted control plane or a non-hosted control plane. So whether running something like GKE, AKS, or EKS. And we can see that about 30% of these failures actually occurred on primarily GKE, because that's the data is a little bit skewed towards 2018 and 2019, and EKS is still fairly recent. But many of these failures would not be prevented by using a hosted control plane. So this is not to say don't use one, but it's to understand that a hosted control plane doesn't protect you from the most common failure modes. So if you are going to use a hosted control plane, remember the resilience engineering concepts to expose the control surfaces of the system. So make sure that you're consuming the upstream logs and metrics. So even if somebody else is managing your control plane for you, you still need to consume those logs. You still need to be able to see what is happening within that control plane to understand where you are within your operating space and within your complex system. There were a couple failures reported due to upgrades, for example, on GKE. So even though you can do a one-click upgrade, don't test it first. And in fact, test everything. Just because you're running on a hosted control plane doesn't mean any less testing. So where I would like to see some of the industry move towards, rather than hosted control planes, is hosting some of the individual components. So an etcd, hosted etcd, would make managing Kubernetes clusters 90% easier, or self-hosting Kubernetes clusters 90% easier. Same applies with the PKI and authentication into those clusters. If that is hosted, those failure modes become a lot more easier to visualize and work around. And then the third one, a little bit close to my heart, is a new project. Well, it's not new, so it's been going for about 1.5 years, is the cluster API within the Kubernetes ecosystem. and that's focused on providing infrastructure agnostic control planes using Kubernetes. So it's Kubernetes on Kubernetes on Kubernetes. And all of the infrastructure providers do have plugins for it. Nobody's yet to offer a hosted version of this. Perhaps VMware's perhaps the exception with their Tanzu mission control, but what this essentially allows you to do is take a lot of the knowledge of managing a control plane, wrap it up in an operator, and then still give you the visibility and the flexibility to respond when issues occur, and put it back in your hands without having to learn too much and get too involved in it. So that comes to the end of the presentation. I'll do a demo now quickly. So there's a list of resources. I can share it with the list afterwards. And the share your failure stories at kth.af. Cool. Are there any questions before I proceed to the open policy demo?
So I see there are a few questions in the chat. So while you're setting that up, perhaps you can answer them. So the first one is from Alice, who's got a quick question with regards to reliability versus resilience. Is there a system in place to best predict when failure can occur?
So by definition, you cannot predict failure, because by definition, you cannot predict the boundaries upon which your system is going to be occurring. So it's not something that you can't predict it. You can, what you can do is try and understand where you are within the system and where your safety boundary is. The further you are away from the safety boundary, the less likely you are to fail, for a failure to occur. That doesn't mean that you're not going to fail. You could be a very, very successful travel consultant yesterday, 2 months ago, and tomorrow you failed. You could have looked at that boundary. Your financial modeling was perfect. You've got 3 years of profit in the bank, and then Corona comes and you bankrupt. So it's not something you can predict, but you can use tools like chaos engineering to understand where those boundaries are and how do you move away from the boundary and how you make the boundary further out. And then just quickly on resilience versus reliability. So reliability is a system performing its duty under known or expected failure modes. So a reliable database cluster will fail over to another database cluster or database server when it fails. A resilient database cluster is going to handle intermittent network connectivity and understand which one is the best to fail over to. So it's a little bit of a distinction there.
All right. So thanks for that. So next one is from Archie, who's got a controversial question. While weighing the pros and cons on using Kubernetes, do you believe the South African IT industry, specifically corporate, is ready to use Kubernetes to its full potential?
Yes. So I think particularly in South Africa, corporates in particular are more than ready for it. And in fact, they're better positioned to make value out of it. So where Kubernetes really comes into play is not as a container orchestrator. So Kubernetes is a container orchestrator, but the real value that Kubernetes brings to the table is providing a language between your developers and your operations, and between your developers and your infrastructure. So if you were working at one corporate and you move to another corporate, how quickly will you be able to deploy your application in the new position? And with something like Kubernetes, you can begin there end on day 1 and begin another role in day 2 and know exactly how to deploy your application. You know exactly how to monitor it. You know exactly how to scale it. You know how to secure it, what policies to apply, and it's that common language that is so universally adopted that is the core value. Whether you're running a container, you're running a VM, you're running serverless, you're running a database, those are the side effects. The primary purpose is the communication, and communication in corporates is shockingly bad. So ticketing hell is unfortunately something that is pretty common. So and more particularly in the South African context, so there is a much larger scarcity of DevOps resources in this country. So where in other countries people might be quite well down their journey on infrastructure as code and making use of cloud environments to lessen that burden. In this country, we're far earlier in that journey. So the amount of value gained from switching from an on-premise deployment model that takes a couple of months to Kubernetes is drastic and massive.
Okay, great. I see that we're short on time for a little bit. There's still one question from Seth. So if you can just quickly answer it before you start the demo. So Seth is asking if there are any best practices on how organizations manage changes to their Kubernetes configuration. So for application code, we have unit tests and CI that verify changes to source code. How does one achieve the same verification or confidence for changes to all of Kubernetes YAML files? So in Ansible and Chef and Puppet world, there's like service spec, inspec. What does K8 have that's similar?
So the open policy agent, and in particular, there's a tool called conf test that will allow you to write tests and policy against your YAML. Okay. So the open policy agent, you can run it as an admission controller in Kubernetes. And when you're running it as an admission controller, it will allow you to define policy that says you cannot deploy a load balancer, or you cannot deploy an ingress unless it's using a specific ingress domain, or you cannot deploy 1,000 replicas of your pod. And it allows you to apply that policy at the admission point, so it will prevent the workload running. And then you can use tools like conf test that will let you shift left on that policy, so to speak. So instead of having that error occur at runtime, you can now push that policy validation into your pipeline and verify your configuration before it actually is attempted to be deployed.
Right. So I believe that's what you're going to show us in this demo, right?
Yes. So this is a little bit more specific around resource management. But Oppa, let me show it to you quickly. So Oppa is an open policy agent. So it is a generic framework for writing rules that do things like authorization, authentication, and manipulation of data. So some of the other use cases are things like row-level security in databases, or authorization on Kafka topics, for file-based access control on Ceph volumes. So it's got quite a number of scenarios that it can be used in. And it uses the Regio language, which is a rule-based language. So what this policy is saying that for any deployment, replication controller, replica set, daemon set, or stateful set, reject the creation of that pod if it doesn't specify resource request or limit. So this is mirroring a little bit what the limit range will do. So a limit range in Kubernetes will let you apply a default resource request. This, on the other hand, will validate that your end users actually need to provide that themselves. If they don't provide it, their pod will not be scheduled. So if I try and...
would you mind just zooming in? Just make the font size a little bit bigger. Yeah.
How is that? So if I have a look at it's a pod that would not be valid. So this is a deployment that does not specify any resource requests. And if I try and deploy it, you'll see I'll get an error message back that says the resource limits or requests are not set. So this is completely configurable in the rules. There's quite a few. There's about 6 or 7 common rules that are deployed across the board, or that are commonly available. So things like ingress, so preventing duplicate ingresses, only using ingresses that you actually have a domain match to. So it lets you apply any of those things. Another good use case of this is in ensuring that your namespaces and resources are annotated, for example, with a service name or a team name, or a billing code or something like that, to make sure that you can do chargebacks. So all of those things are pretty easy to do. So this was the example of a resource request. And then if I look at one that will actually go through, so if I look at this deployment defines resource limits and requests. And then if I want to run it, it will get accepted. So you can apply these on the resources, pretty much anything. So it works, if you look back at the policies, so it works on the object that is being admitted. So in this case, input request kind. So input request would be your Kubernetes object. And then you can run any validation on it. You can pull in data from other sources. So you can load, for example, a list of valid team names or a list of valid billing codes that you're allowed to apply, and then use that to validate, to make sure that your resources are okay to run. So that is a very quick run through on open policy. I can show you. So it uses an admission controller. And what the admission controller looks like is this is validating webhook. And what it will do is the admission controller will run as a, from a Java world, as like a pre or post hook. And it will run on your selected objects, and it'll let you either validate that they're valid or not. If you're running a mutating webhook, which you can use. So I know Goldman Sachs use Open Policy Agent with a mutating admission webhook, where they will then, based on the namespace that's created, then go and create relevant objects in that namespace based on some predefined criteria, whether those are resource quotas or limit ranges or ingresses, or whatever they are. Yes, I think that's about it.
Oh, thanks, Moshe. Thank you so much. I see we were very, we were over time by quite a bit. I'm just going to quickly do our raffle draw.
Sure.
And, people can ask questions in the meantime while I figure out how I'm going to do this draw. Oh, by the way, if you want to ask a question, you can unmute yourself. The floor is open. Okay, I'm just going to share my screen. I think what I'm going to do is just going to use a random number generator on Google, and let's see how this is going. Where's my Zoom now? I don't know. What happened to my Zoom?
Well, we can still hear you.
Yeah, so I haven't. Hold on. Where is it? Can someone help me and tell me where I can go to? I'm looking for the Zoom window. Oh, okay.
Why do you need a Zoom?
Hold on.
Fine. Just do the
Okay.
generator.
All right, it's cool. I'm just going to generate. Sorry, I can't share my screen and look at the participants at the same time. So if we have 18 participants, I'm just going to quickly generate. Between 1 and 18. Let's see what number it gives us. Okay, 12. And then I'm just going to count the 12th participants. I'm sorry about that. This is, I really don't know how to use Zoom. Just going to quickly check. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is Michelle Taylor. Okay, great. So Michelle, well done. You just won yourself a JetBrains license.
So thanks, Sid.
All right. Yeah. So I'll have your email. Then I'll just email that license to you. Cool. So yeah, the floor is open. If you guys have any questions, you can direct them now to Moshe.
One question from me, Moshe. Can you hear me? Yeah, hello?
Yep, I can hear you just fine.
The open agent policy, does it only look at your resource YAMLs, or can you dig down further into, for example, running containers to see if they're running as root or are they running as a user? Can you use open agent policy for that?
So, so there's two different things. So there's the engine, which will take a set of input and a set of policy and give you an output. And that is most commonly deployed as an admission controller. So, which means that you can, at the point at which you create the container, you can then say, okay, you may not run as root, or you can only run as root if you're using this image, or you cannot run images that are not from our internal registry, for example. But once that container or pod is deployed, it doesn't have any view of that. And I'm not actually sure if there's anything that will do it. There was something from T-Mobile called MagTape that was a bit of a higher level of abstraction that may be able to look at an existing cluster and tell you if your new policies will validate or not validate against any of those objects. And then apply,
Okay, cool.
and then I think it can do like alerts to Slack as well. So it's not a tool that I've tested just yet, but it's something that's very near at my to test list because it does solve that problem as well.
Cool, sounds good, thank you.
Sure.
So on the topic of OPA, I've got a question, right? You using the OPA admission controller? I know that OPA has a new project called Gatekeeper. Are you going and using Gatekeeper?
So Gatekeeper, it takes a little bit more of a Kubernetes view where it allows you to create, I think, like these Kubernetes CRDs that define policies at a little bit of a higher level of abstraction. But like, so for me personally, I don't really see much of the value there over just using the Regio. Or Rego, I don't know how to pronounce it. So, but it delivers the same thing. It's like you prefer Java or Scala.
Yeah, cool, thanks. Anyone else has a question?
So if nobody has a question, can I ask a couple questions of the wider group? So I'll go ahead. So what are people's current challenges with running Kubernetes? And if you're not running Kubernetes, why not? or is everybody running Kubernetes very smoothly with no problems?
So I don't know if the silence means everyone is running Kubernetes smoothly or no one is running Kubernetes. I'm not too sure, but I have one. So the biggest challenge for me running Kubernetes is just dealing with lots of distributions. A lot of the times, like you don't know which one to use because there's just like so many options. You know, like you mentioned, you can use a managed service Kubernetes or you can do it yourself. So, what do you think someone should do when you have if you're given a myriad of choices of Kubernetes distributions? Like, what's do you have any guidelines in terms of choosing these distributions? What is your take on it?
So I always will look at this from a resilience engineer's perspective. So I want to, from any distribution, I'm going to evaluate it against how flexible it is and how capable it is to adapt to a changing environment. So what are the options that I can use? What are the different scenarios I can use it under? What can I change? What can't I change? What can I see? What can't I see? So the more I can change, the more I can see, the more flexible it is. You still need to balance that with the 300 or so Kube API server options that are available. So you do want some sensible defaults and best practices built in, but at the same time, you don't want to handcuff yourself and be stuck in a very narrow place where you might actually need to go out a little bit. So that's my view. So the hosted control planes will give you the least flexibility. When you're using a hosted control plane, for example, try and look at it from that perspective of what are the options that are available to me. What can I see inside that control plane? And with the distribution, the same applies. What can I configure? So maybe you don't need to enable a feature flag to deploy your application. But what happens if your application is under a corona load and one of those feature flags is going to take you from a 5-second response time to a 1-second response time? So that's not something that you can know in advance. That's something that you will need to react to afterwards.
Cool. I see that Tom has a question. So he's saying that scaling is an issue. It can get quite big quite quickly. Do you have any comments on that?
Yeah, so scaling is always an issue. So I don't think anybody has really solved this, including Google. So on the one hand, you can scale prematurely and then you cost too much money, or you can wait to scale and then you're going to be under a bit of load. So probably, so Kubernetes can scale to about 10,000, as far as I know, 10,000 nodes and tens and tens of thousands of pods, hundreds of thousands of pods. So it's not really a question of can Kubernetes scale, it's can the environment and context in which you're working with. And there, if you're using things like cluster autoscaler or horizontal pod autoscaler, try scale on business metrics and not artificial metrics like CPU and memory usage, which aren't really an indication and can lead to run array scaling. So scale on business metrics, response time as observed at the browser layer if you have access to it, or otherwise at your ingress layer or some other user-facing metric rather than a CPU metric. I would say that's probably the best advice I could give.
Cool, thanks. Guys, if you don't have any questions, Just gonna end this meeting, in the session. No one? Okay, so yeah, so thank you, Moshe, for delivering this insightful and comprehensive session on Kubernetes failure modes. Yeah, I think if you don't mind, I don't know if any of this stuff is copyrighted. Can I share it?
Nope.
Okay,
Yeah.
cool. So I'll probably
And I'll actually try and share the slide deck as well.
that would be perfect. Yeah, so I'll make an announcement on our events page about that. Just share the link with everyone. Okay, cool.
Yep.
Thanks everyone for joining us. Yeah, and that's it. Hope to see you guys in the June meetup. Cool. Thanks a lot, guys.
Cheers, everyone.
Cheers, everyone.
Cheers.